So this is section 3B, and we're on part 2. We're looking now at our second derivative and what it tells us. And it turns out it's going to give us information about something called the concavity and inflection points. Let's start by talking about concavity. A graph is concave up if it bends upward. Sometimes we think of it as a shape that holds water. If you imagined rain falling on this graph, what areas would the water collect in? Those are the areas where the graph is concave up. So if I were to try to mark those areas on my graph, I'm going to say that roughly from about here all the way to here, I would have an area where the graph is concave up. Now it continues to be concave up until I get roughly here. And then it's going to start being concave down for a while. But then maybe about here again, we've got our graph concave up again. So concave up, bending up. The concave down portions, of course, are just the opposite. So let me mark those as well. Concave down for this graph would be all the way through here, and then again this little section. You can imagine the rain would just kind of run off those sections. It wouldn't collect. All right, well, let's see what the second derivative has to do with those. If you imagine, and let's start by looking at the areas where the graph is concave up. I'm going to look at this little area in here. I'm just going to sketch a few little tangent lines in this area. What do you notice about the slopes of those tangent lines? It starts negative, it got positive, it got bigger, and it even got bigger. So the first derivative is actually increasing. The first derivative gets bigger and bigger in areas where the graph is concave up. So the first derivative is increasing in these areas. Well, as we just saw in the last video, if something is increasing, then its derivative is positive. So the derivative of the first derivative's derivative, or in other words, the second derivative, is positive. So a second derivative being positive indicates an area of the graph that's concave up. I'm sure you can predict how we know when it's concave down, but let's just look at the geometry once. If we have tangent lines in an area where the graph is concave down, notice how they're getting less and less steep. So the slopes or the derivatives are decreasing. Our graph is concave down if our derivative is decreasing. Oops, sorry, that should have said down. Well, as again, we just saw in the last video, if something is decreasing, then its derivative should be negative, right? So, what's true about the second derivative in areas where the graph is concave down? The derivative of the first derivative, or in other words, the second derivative, would have to be negative. So on my graph, I know that all throughout this entire pink region, f double prime is positive, and again over here, f double prime is positive. And in these blue parts where we're concave down, f double prime would be negative. So what do you think happens right at the points where we change from concave up to concave down? Right, there'd be some point right about here where the graph was concave down and it changed to concave up. It's got a name. It's called an inflection point. Or IP for short. And there's a couple more of them over here, right? There's one here. And there's one here. Well, we know at those points the second derivative can't be positive and it can't be negative because at those exact points we're neither concave up nor concave down. We're kind of in between. So it would make sense that the second derivative would be negative at those, the second derivative would be 0 at those points. It's also possible that the second derivative is undefined at those points. And so we're going to have the same conditions on a critical point as we did for max-mins. An inflection point, or point of inflection on a graph, is a point where the graph changes concavity. And we say that x equals c is a critical value if the second derivative is either 0 or undefined. If it's anything else, we already know if it's concave up or down, right? So x equals c is an inflection point. If we either change from concave down and negative to concave up a positive second derivative, or could be the other way around, right? It's still an inflection point if we change from concave up a positive second derivative to concave down a negative second derivative. But what we have to have is a change. We have to change the sign of the second derivative. If there's no change, if it's positive, positive, or negative, negative, then the critical value turns out not to be an inflection point at all. So we're going to go back to that same function that we were working with a little bit ago, this cubic polynomial. We've already found the maximum and minimum points. Now we're going to find all the inflection points, and then we'll use that second derivative to list the intervals where the graph is concave up and concave down. Eventually, we'll use all of that information to sketch a graph. So just as a reminder, the derivative was 3x squared minus 6x minus 24. So my second derivative is going to be 6x minus 6. Again, I don't have to worry about that being undefined. So my critical values will occur when that second derivative is equal to 0, which would be when x is equal to 1. So I only have one critical value for the second derivative. Let's test it. I'm now testing the second derivative, f double prime. I already know it's 0 here. And my second derivative is pretty easy. It's just 6x minus 6, so maybe I can plug it in my head this time. Let's plug in 0, something to the left of 1. 0 minus 6 would be negative. And let's try 2. 6 times 2 would be 12 minus 6. That would be positive. So my function is concave down on this side and concave up on that side. And since it did change, I have an inflection point at x equal 1. If I want the y value at that inflection point, I should go all the way back to the original. I think it's still in here. Yeah, I still have my function in here, so if x is 1, looks like y is negative 16. We can use the same little chart to list the intervals where we're concave up and concave down. Concave up would start at 1 and go all the way to infinity. Again, an interval of x values. And concave down would be here from negative infinity to 1. All right, let's see if we can put all of this information together and draw a nice graph of this function. I'm going to go ahead and bring in my other little pieces of information, at least about the maximum and the minimum, from the previous analysis that we did. In the last video, we had found that there was a local maximum or a relative maximum at negative 238 and a local minimum at 4, negative 70. So we'll use that information as well and see what we can do. Let's see here. I gotta have some pretty large y values on this, large and small, so I'm gonna go by tens. 10, 20, 30, 40, 50. And same down here. All right, I'm going to plot the special points, starting with the inflection point. 1, negative 16 would be about there. And next I'll plot the maximum, negative 238, right around here. And then the minimum, 4, negative 70, would be about there. Now, if I wanted even more accuracy, I could do things like find x and y intercepts and things like that. For the purposes of what we're going to do here, I'm going to go ahead and just sketch. But again, there's more information that you could get if you wanted to be even more accurate. All right, so I'm going to start out. I know I'm going to begin concave down, and I'll go through this maximum and stay concave down until I hit the inflection point. Like so. At that inflection point, I'm going to change to concave up, and then I'm going to go down and go through that minimum. Okay. I have stopped short of committing to where I want to go through the x-axis. Maybe I'll use a graph on my calculator to verify that, or Desmos or something like that. But you get the idea. This graph would just keep going down forever and keep going up forever. Okay. Let's actually go ahead and verify what we just did using a Desmos graph. If I go ahead and put in my function, and find myself a window that fits that a little bit better, we know that x has to go down to at least negative 70. Maybe I'll go negative 80 just to give myself a little space. And we'll go up to positive 80 as well. There we go. And I can see that just before negative 4 was one of my intercepts. Between 0 and 1, and again a little bit past 6, we could get some values if we wanted to from the Desmos graph. And I could just use that to kind of fill in the rest of my graph. Notice here this maximum, negative 238, just like we expected, and this minimum for negative 70, also just what we expected. The inflection point is subtle. You can't see it perfectly, but you can definitely tell that we were concave down for a while, and here we're concave up. So somewhere in between is the inflection point. So I'm going to go ahead and use that graph just to kind of finish out, get my x-intercepts a little bit more accurate, around negative 4 and a little past 6. And so there's a decent graph of my function. Again, we were able to predict something that we've never been able to do before, the location of the maximum and minimum points without using technology, right? Before we could find the vertex of a parabola using our special vertex formulas, but we haven't been able to do a maximum and a minimum point. And now we've been able to do that using calculus. We've also added the information about an inflection point that we don't really talk about usually in other math classes. All right, let's finish this part of the video up with a summary of everything we've just said. For each of these features on the graph, how do we know about them using a derivative? So the graph is increasing if the derivative is positive, and the graph is decreasing if the derivative is negative. We have a relative maximum if two things happen, right? First of all, f prime is 0 or undefined, and we have to go for a maximum from increasing, so f prime positive, to decreasing, f prime negative. Relative minimum is exactly the opposite of that. We still have to have our derivative be 0 or undefined, but this time we want to go from decreasing to increasing to get a minimum. So f prime is negative on the left side and positive on the right side. All right, all of those are parts of what we're calling our first derivative test, which I'll often abbreviate as FDT, first derivative test. When we get to concavity and inflection points, this is now stuff that our second derivative tells us about, so I'm going to call this second derivative test. Our graph is concave up if the second derivative is positive, and it's concave down if the second derivative is negative. For an inflection point, the second derivative has to be 0 or undefined, and in addition, we have to have a change in concavity. It doesn't matter whether it goes from concave up to down or down to up, but it does have to change. So the second derivative must change signs at the inflection point. All right, we will pause there and then we'll come back and do a few examples, start to finish, of using derivatives to inform us about what graphs look like.